Good morning, good afternoon, and good evening to everyone who joins us from around the world. We're so glad you're here.
It's wonderful to be here and to be exploring this topic with all of you.
This is Andrew and Renee. Welcome to the SAC series.
Great to be back.
Today we are exploring the mathematical universe hypothesis. And I have to say, getting ready for this one, it's been something else.
It's a bit of a mind bender, isn't it?
It's putting it mildly. I was staring at my coffee mug this morning and had this genuinely weird moment where I thought, is that a thing? Or is my brain just projecting a mathematical cylinder onto some raw data because it's easier?
Well, that's a dangerous path to go down before you've had the coffee that's in the mug.
Tell me about it. But that's exactly the kind of territory we're getting into today. We're not just talking about physics in the usual sense, black holes, quarks, that kind of thing.
How this goes deeper. This is about the fundamental nature of reality itself. What is it all made of?
And the hypothesis on the table, the one really championed by cosmologist Max Tegmark, is that everything, this table, the microphone, you, me, the air, it's not stuff in the way we normally think about it.
Right. The radical idea is that we are not living in a universe that is simply described by mathematics. The claim is that we are living inside a mathematical structure.
It sounds like science fiction.
Yeah.
Like we're all going to find out we're characters in a cosmic computer simulation.
And we will get to that idea. But before we, cause an existential crisis for everyone listening, we should probably start at the beginning.
Right. Because this idea, in some form, has been around for a very long time. Didn't just pop out of nowhere with quantum mechanics.
Not at all. It really starts with the birth of modern science, with this observation that nature seems to speak a certain language.
Galileo,
yes. And he had this beautiful line. He said, "The universe is a grand book, which stands continually open to our gaze."
I remember hearing that in school.
We all do. But he adds a crucial condition. He says you can't read the book unless you first learn the language and the characters in which it's written.
And that language is mathematics.
That language is mathematics. And when you really stop and think about that, it's weird. It's profoundly strange. Why should the orbit of a planet or the arc of a thrown stone obey these clean, abstract rules that humans came up with?
Exactly. I mean, math is something we invent, right? We sit down with a pencil and paper, we draw some squiggles, we make up rules, we decide that 1 + 1 = 2.
These are abstract concepts. They live in our minds. You can't, trip over the number 7 on the sidewalk. It doesn't have a physical form.
I've tried. It's impossible.
And yet these purely mental inventions, these scribbles on a blackboard, somehow predict the behavior of the universe with what can only be described as terrifying accuracy.
And that's the perfect lead-in to Eugene Wigner, because he looked at this fact and basically said, everyone, you are not being surprised enough by this.
That's a great way to put it. Wigner was a Nobel Prize-winning physicist, and in 1960 he wrote this seminal paper. The title alone tells you everything. The Unreasonable Effectiveness of Mathematics in the Natural Sciences.
Unreasonable. Not just effective, but unreasonably so.
Exactly. And his point was that there's no logical reason it should work this well, or even at all. He pointed out that mathematicians are often just playing. They're like artists exploring abstract structures for their own internal beauty and consistency.
They're not trying to describe the real world.
Not at all. They're just following the rules of logic to see where they lead. It's a game, a really complex, beautiful game.
Like someone inventing the rules for chess. They're not trying to model a real battle. They're just creating a self-contained system.
Precisely. Now imagine you invent a game like chess. You create all the rules, the pieces, the board. It's just for fun. And then 100 years later, astronomers discover a new solar system, and they realize the planets are moving exactly according to the rules of chess.
That would be unsettling, to say the least.
That is what happens in physics all the time. It's this recurring miracle.
Let's get into a concrete example. The one from the stack about geometry is, I think, the most powerful.
Non-Euclidean geometry. It's the perfect case. For 2,000 years, since ancient Greece, we had Euclid's geometry. It was considered absolute truth.
Right. The stuff you learn in high school. Parallel lines never meet. The angles of a triangle always add up to 180 degrees. It's just how space works.
It was thought to be self-evident. But then in the 19th century, you get these mathematicians, Gauss, Riemann, Lobachevsky, and they start asking these heretical what-if questions.
What if that's not the only way?
What if parallel lines can meet? What if you draw a triangle on a curved surface, like a sphere? Suddenly, the angles add up to more than 180 degrees. They were just playing with axioms, seeing if they could build a consistent system that broke Euclid's rules.
They were just making up a mathematical toy, a curiosity.
A toy, that's the word. It had no known application to reality. It was pure abstraction. Then, decades later, a young Albert Einstein is wrestling with the problem of gravity.
And his theory of general relativity isn't working with standard flat Euclidean geometry.
It's failing. He realizes that massive objects must be curving the fabric of space itself, and he needs a mathematical language to describe this curvature. And where does he find it?
Sitting on a shelf, collecting dust. Riemann's geometry.
The exact tool he needed had been invented 50 years earlier by a mathematician who was just playing around. The math was there, waiting for physics to catch up.
It's just spooky. It feels like the universe came with a user manual, but it was written in a language we had to invent first before we could read it.
And it gets even stranger when you go into the quantum world. Let's talk about complex number.
Oh boy. The imaginary number I. The square root of -1.
Yes. Now, logically, from a simple physical point of view, what number, when you multiply it by itself, gives you a negative number?
Nothing. A positive times a positive is positive. A negative times a negative is also positive. There's no number on the number line that works.
Exactly. It's an impossibility in the real world of canning things. That's why they were originally called imaginary numbers. It was an insult, a term of mockery. They were seen as a weird algebraic trick, a useful fiction, but certainly not something that would show up in the real world.
But then quantum mechanics happened.
Then Erwin Schrödinger tried to write the fundamental equation describing the behavior of an electron, a real physical thing.
The Schrödinger equation.
And he tried to do it with real numbers. The equation just didn't work. It failed to describe what was actually observed. And he realized, almost against his will, that the only way to make the equation work
Was to put the imaginary number right in the heart of it.
he had to use this mathematical glitch to describe the foundation of reality. The fundamental equation that governs everything from your phone to the sun has a number in it that shouldn't even exist in the physical world.
So this is what Wigner meant. He called it a wonderful gift which we neither understand nor deserve. It borders on the miraculous.
It really does. But we have to be fair. We have to introduce the skeptic at the party.
Right. Not everyone is on board with the miracle explanation. Enter Richard Hamming.
Hamming came along later and basically said, hold on, let's not get carried away. He wrote a response arguing that this effectiveness is actually, well, pretty reasonable when you think about it.
And his first point is what's called the selection effect, right?
Yes. He says, we're just focusing on the successes. We see that Riemannian geometry works for gravity, and we shout, miracle, but we're ignoring the vast, vast libraries of mathematical structures that have been invented and have absolutely no application to the physical world.
So it's a form of cherry picking. We develop thousands of mathematical tools, and every now and then one of them happens to fit a physical problem, and we act surprised.
We're counting the hits and ignoring the misses. That's part of his argument. But he has a more subtle and I think more powerful point about evolution.
Okay, this one is really interesting.
Hamming's point is that our brains didn't evolve in a vacuum. We evolved in this universe. Our entire neural architecture was shaped by the physical laws of this world in order to survive.
Right. If you're an early hominid, you need to be able to, say, throw a spear and hit a moving target.
Exactly. You need to intuitively understand trajectories, speed, distance. Your brain has to be a pretty good physics calculator, or you starve.
Or you get eaten because you can't judge how fast that lion is running.
So natural selection has hardwired our brains to recognize the patterns of nature. Hamming argues that the math we invent is just a formal, abstract extension of that built-in pattern recognition.
So, of course, our math describes the world well. We were built by the world to understand it. The tools fit the job because the job made the tools.
That's a perfect way to put it. It flips the mystery on its head. It's not that the universe is mathematical, it's that our brains are physical. We have, you might say, physics goggles on.
It's the old saying, if all you have is a hammer, everything looks like a nail. If your brain is a pattern-recognizing machine built by physics, everything looks like a physical pattern.
It's what Hamming calls baking it in. We create models based on the tools we have. If we're good at thinking about linear relationships, we're going to see linear relationships everywhere.
That makes a lot of sense. It feels less spooky, more grounded. But does it explain everything?
That's the question.
I mean, I get that evolution explains why I can catch a ball. But does it explain why we can formulate something as abstract and non-intuitive as quantum field theory?
And more to the point, does it explain the precision? This is the killer counter argument. Evolution is about being good enough to survive. You don't need to calculate a spear's trajectory to 10 decimal places.
You just need to hit the mammoth, roughly.
But the magnetic moment of the electron, a property of a fundamental particle, has been measured experimentally. And it has been calculated using the mathematics of quantum electrodynamics. The two numbers, the measurement and the prediction, match to an accuracy of 1 part in a trillion.
To more than 10 decimal places.
That kind of absurd pinpoint precision seems to go way beyond what a survival instinct would bake into our brains. It suggests the connection between the math and the reality is not just an approximation.
And that feeling that the connection must be deeper is what brings us to Max Tegmark.
Exactly. Tegmark looks at this whole debate, at Wigner's miracle and Hamming's skepticism, and he says, you're both just nibbling at edges of a much more profound truth.
He takes Wigner's idea and turns it up to 11.
He takes it to its ultimate logical conclusion. He doesn't say math describes the universe. He says the universe is mathematics.
This is the mathematical universe hypothesis, the MUH.
And his core thesis is deceptively simple. Mathematical existence is the same thing as physical existence. There is no difference. If a mathematical structure is internally consistent, then it exists physically somewhere.
Okay, we need to walk through this slowly because that is a huge leap. How do you get from this equation is a good model for Mars's orbit to Mars is the equation?
The logic starts with a very simple assumption that almost every scientist makes. He calls it the external reality hypothesis, or the ERH.
Which sounds pretty basic.
It is. The ERH just says that there is an external physical reality that exists completely independently of us humans.
I think most people would agree with that. If all of humanity vanished tomorrow, the Andromeda Galaxy would still be on a collision course with the Milky Way. The universe doesn't need an audience.
Right. So if reality is independent of us, then a complete final description of that reality, a theory of everything, must also be independent of us. It can't contain any human-centric concepts.
What do you mean by human-centric concept?
He calls it human baggage. Think about the words we use in physics. We talk about particles, waves, observers, redness, heaviness.
Okay.
All of those words are loaded with human baggage. Redness is a subjective experience created by our eyes and brains. Heaviness is a feeling in our muscles. Even a particle is just a metaphor based on our experience with tiny rocks or grains of sand.
So to get to the true nature of reality, you have to describe it in a way that an alien intelligence with completely different senses and experiences would understand.
An alien intelligence, or even just reality itself when nobody's looking. You have to strip away all the baggage, all the metaphors, all the cultural context, all the sensory words.
And if you peel away all that human language,
Yeah.
what's left?
What is a description that is completely free of subjective baggage? Tegmark argues there is only one answer. A mathematical structure.
Nothing else.
Nothing else. A mathematical structure is just a set of abstract things and the relationships between them. The number 2 is related to the number 4 by the relation is half of. That's it. It's pure abstract relation. It's the only truly baggage-free language we have.
So the logic chain is, if an external reality exists, its true description must be free of human baggage. The only baggage-free description is math.
Therefore, external reality is a mathematical structure. The map and the territory are the same thing.
He uses a chess analogy that I found really helpful for this.
The chess analogy is perfect. So you can describe a chess game in a story-like way. You can say, the valiant knight on his noble steed leaped bravely over the cowering pawn to threaten the evil queen.
That's the baggage. We're projecting human concepts like bravery and evil onto the pieces. They're not actually in the game.
They're not. That's our narrative overlay. But you can also describe the exact same move using algebraic notation, NB1 to C3.
Just coordinates and rules.
Just coordinates and rules. And an alien who has never seen a horse, never heard of a queen, has no concept of medieval warfare. They could understand the game perfectly from the algebraic notation. They could become a grandmaster.
Because for them, the knight isn't a horse. It's just an object defined by its rules of movement. Its identity is its mathematical function.
Precisely. And Tegmark's argument is that the universe is just a vastly more complicated game of chess. We look at an electron and we tell a story about a tiny spinning ball of negative charge. That's the baggage.
That's the valiant knight story.
Yes. The actual reality of the electron, the baggage-free description, is just its list of properties. Its mass, its charge, its spin, and what are those things?
They're just numbers. properties defined by mathematics.
An electron is just a set of numbers at a particular space-time coordinate. And that idea connects to the deep philosophical theory that really powers this whole hypothesis. It's a field called ontic structural realism.
Or SR. Okay, break that down for us. Ontic.
Ontic means it's a claim about what is real, about being, or existence itself. So OSR is the claim that what's fundamentally real is the structure, the network of relationships.
Not the things in the network.
Exactly. This is completely backward from how we usually think. We tend to think that objects are primary. You have a baseball, and it has properties like mass and roundness. The ball comes first.
Right. You can't have a relationship like is heavier than without two things to relate.
That's our intuition. But OSR, especially the more radical versions, says that in fundamental physics, it's the other way around. There are relations without relata. The relationships are what's real, and the things are just convenient fictions.
So, how does that work? How can you have the marriage without the two people?
The analogy often used is a family tree. You are defined by your relationships. You are a son, a brother, a cousin, a nephew. We think of you as a person who has all these relationships.
Of course.
But OSR would argue at the fundamental level of an electron that the particle is just the sum total of its relationships. It is its mass, its charge, its spin, its position relative to other particles. If you could somehow strip away all those relational properties,
there'd be nothing left in the middle. There's no nugget of electron stuff.
There's no nugget. The thingness dissolves, and you're left with just the structure, just the web of connections.
And this ties into that weird quantum idea of haecity, or thisness.
Yes, haecity is the philosophical term for what makes an individual thing uniquely itself, even if it's identical to another thing. If you have two factory-made billiard balls that are perfectly identical, they are still two distinct objects. You can paint one red to tell them apart. They each have their own thisness.
But you can't do that with electrons.
You absolutely cannot. In quantum mechanics, fundamental particles are truly perfectly indistinguishable. If you have two electrons in a box and you swap their positions, the universe is not just similar, it is unchanged. They have no individual identity.
You can't name one Bog and the other Susan.
You can't, and this is a huge piece of evidence for OSR. They don't have a core thisness. Their entire reality consists of their shared properties and their role in the overall structure. They are placeholders in the math.
Okay, so if the universe is just a mathematical structure, and we know there isn't just one possible mathematical structure.
Now you're making the final leap.
It leads directly to the multiverse, doesn't it?
It's the inevitable conclusion. If physical existence is identical to mathematical existence, then every single mathematical structure that is self-consistent must also exist as a physical universe.
And this is what Tegmark calls the level 4 multiverse, the big one. But let's set the stage. Can you give us a quick rundown of his first 3 levels of the multiverse so we see how he built up to this?
Absolutely. The levels are a hierarchy of increasing weirdness. Level 1 is the most straightforward. It just assumes that space is infinite.
Which is what our best cosmological data suggests.
Right. And if space goes on forever and there's a finite number of ways particles can be arranged in a given volume, then eventually those arrangements have to repeat.
It's like having an infinite number of monkeys on an infinite number of typewriters.
Yeah.
Eventually, one of them will type Shakespeare.
Exactly. So infinitely far away in our own universe, there is another region of space identical to ours. Another Earth, another you, another me having this exact conversation, and infinite variations of it.
Okay, that's just probability in big numbers. What's level 2?
Level 2 comes from the theory of eternal inflation. The idea is that our Big Bang wasn't the only one. The multiverse is like a giant, eternally expanding block of dough, and little bubbles of space-time are constantly popping into existence within it. Our entire observable universe is just one of these bubbles.
And the other bubbles could have different physics.
They could have different physical constants. Yeah. The fundamental equations might be the same, but the settings on the dials could be different. Maybe the speed of light is faster in one, or the strength of gravity is weaker in another.
Different flavors of universe. And level 3.
Level 3 is the famous many-worlds interpretation of quantum mechanics. This one happens right here, all around us, all the time. Every time a quantum event has more than one possible outcome, the universe splits into parallel branches.
So if an atom has a 50-50 chance of decaying, in one universe it does, and in another universe it doesn't.
And both universes are equally real. One you experiences the decay, the other you doesn't. But Tegmark says these 3 levels, as wild as they are still just variations on a theme.
They're all living under the same basic mathematical superstructure.
Yes. Level 4 is the ultimate step. It's what he calls the ultimate ensemble. It's the multiverse of all possible mathematical structures.
So we're not just talking about different particle arrangements or different physical constants. We're talking about completely different fundamental laws.
Completely different operating systems. There is a universe that is perfectly described by simple Euclidean geometry. There's a universe that operates on a different kind of logic. There are universes whose mathematical foundations are so complex and alien, we haven't even conceived of them yet.
If you can write down a set of mathematical rules that doesn't contradict itself.
Then it exists as a physical reality. Somewhere.
Why do we need to go that far?
Yeah?
That seems like an explosion of, well, everything. Why propose this?
Because it offers a potential solution to one of the deepest mysteries in cosmology. The fine-tuning problem.
The Goldilocks problem. The fact that our universe seems bizarrely perfect for life to exist.
Exactly. Physicists have found that if you tweak the values of the fundamental constants like the strength of gravity or the mass of the electron by even a tiny, tiny fraction,
The whole thing would fall apart.
if the strong nuclear force were a bit weaker, stars couldn't ignite. If the electromagnetic force were a bit stronger, protons would repel each other so much that atoms couldn't form. The universe seems balanced on a razor's edge.
And the question is why? Why do we have these specific life-permitting numbers? The traditional answers are either we got absurdly lucky or some intelligent designer set the dials.
But the level 4 multiverse provides a third option. It says there's no luck and no designer.
It says that all the possible dial settings exist in their own universes.
All of them. There are countless dead universes where gravity is too strong and they collapse back into a black hole instantly. There are countless empty universes where atoms could never form. They exist. But of course, there's no one in them to observe how boring they are.
We can only find ourselves in the universe that has the right conditions to create observers.
It's a form of the anthropic principle. A fish shouldn't be surprised to find itself in water. We shouldn't be surprised to find ourselves in a universe that allows for our existence.
So the question, why these laws, is the wrong question.
The MUH says the question is, why are we in this universe out of all the possibilities? And the answer is simply, because this is one of the ones where anyone can ask the question.
It reframes the goal of physics. We're no longer searching for the one true law that God chose. We're trying to find our own address in this vast landscape of all possible laws.
It's like we're living inside the Library of Babel, the Borges story.
A library with an infinite number of rooms and books containing every possible combination of letters.
Yes. Almost all the books are complete gibberish, just random strings of characters. But somewhere in that library, one book contains the complete text of Hamlet, and another book contains the complete physical laws of our universe.
And we're just the inhabitants of that particular book. That's a staggering thought.
Yeah.
It is. But it raises a huge problem. A mathematical structure, like a triangle, or the number pi. It's static, it's timeless, it doesn't do anything, it just is.
But our universe isn't static. I'm talking you're gesturing. Things are happening. Time is clearly passing. So how do you get change in the flow of time out of a static mathematical object?
This is where Tegmark introduces one of his most important concepts. The difference between the view from the outside and the view from the inside. He calls it the bird's perspective versus the frog's perspective.
Okay, the bird and the frog. Let's break this down.
The bird is the external observer, the bird's eye view. From this perspective, you are looking at our entire universe, all of space and all of time, as a single, complete object.
A four-dimensional block of space-time.
Exactly. Think of it like a DVD on a shelf. The whole movie, beginning, middle, and end, is contained on that disc. All at once, it's a static object. That's the bird's view of our universe. The past, the present, and the future are just different locations within this static block.
So from the bird's perspective, the dinosaurs, this conversation, and the heat-death of the universe all exist simultaneously. They're just different coordinates in the object.
Correct. For the bird, there is no flow of time. It's a timeless, unchanging mathematical structure.
But I'm not the bird. I feel time passing very acutely.
Because you are the frog, you are a self-aware substructure inside the mathematical object. You are a character living within the movie on the DVD.
And as a character, I experience the movie frame by frame. Scene 1 leads to scene 2.
Yes. Your consciousness processes the information in the structure sequentially. You have memories of the past frames, and you have no information about the future frames. This creates the powerful illusion of a flowing present moment moving from a fixed past to an open future.
But it's an illusion of perspective. The future frames are already on the disk. They're already part of the mathematical structure.
They are just as real and fixed as the past frames. You just haven't gotten there yet from your frog's perspective.
This is the block universe theory, and it has huge implications for things like free will.
It certainly seems to. If the future is already written, already part of the static block, then in what sense are our choices free?
My feeling of agonizing over a decision is just me arriving at a pre-written point in the script. The feeling of choice is real, but the choice itself was already determined as part of the structure.
That's the implication. It can be a deeply unsettling idea, or for some a liberating one. The stress of the future is gone, because the future is just another place.
It also completely changes our idea of randomness, especially in quantum mechanics. We're told that's where true randomness lives.
God does not play dice, as Einstein famously objected. In the MUH, Einstein is right. From the bird's perspective, looking at the entire mathematical structure, there is nothing random. It's a perfectly defined, deterministic object.
So why does it look random to us frogs?
Because of our limited information, it's like looking at the digits of pi. They seem to be a random sequence. There's no discernible pattern, but they're not random at all. They're rigidly determined by the definition of a circle. We just can't see the whole pattern from our limited viewpoint.
So quantum uncertainty is what philosophers call epistemic. It's a lack of knowledge on our part, not unentic, meaning a true fuzziness in reality itself.
Exactly. The uncertainty is in the frog's head, not in the bird's world.
And this must also do away with the idea of a beginning, right? The Big Bang as a creation event.
It reframes it. In the block universe model, the Big Bang isn't a moment when the universe was created out of nothing. It's simply the boundary of the mathematical object.
Like the starting point of a ruler, the 0-inch mark.
Perfect analogy. The 0 mark didn't create the rest of the ruler. It's just the edge of the shape. The Big Bang is simply the edge of the space-time manifold where the time coordinate is 0. The structure doesn't start, it just is.
Wow, that's elegant and a little bit terrifying. It replaces creation with geometry.
It does. But as elegant as it is, we have to be good scientists and philosophers and look for the problems. And there are some very big ones.
And the biggest one, ironically, comes from mathematics itself, from a man named Kurt Gödel.
Gödel's incompleteness theorems. This is a potential showstopper for the MUH. In the 1930s, Gödel proved something that shook the foundations of mathematics and logic.
He proved that math is, in a way, broken, or at least incomplete.
That's a fair way to put it. He proved two things. First, in any mathematical system complex enough to include basic arithmetic, there will always be statements that are true, but which cannot be proven to be true within that system.
There are mathematical truths that are forever beyond our reach.
And second, and maybe even more devastatingly, he proved that no such system can ever prove its own consistency. You can never be 100% sure that the rules won't eventually lead to a contradiction, like proving that 1 equals 2.
So if our universe is a mathematical system, does that mean it contains physical truths that are unprovable? Or worse, could our universe be inconsistent and just crash one day?
A cosmic blue screen of death. It's a serious philosophical problem. If the universe is math, then it seems it must inherit math's incompleteness and potential inconsistency.
So how does Tegmark deal with this? Does he have a response?
He does. He proposes a slight retreat, a modification he calls the computable universe hypothesis, or CUH.
So it's a patch to fix the Gödel problem.
It is. He suggests that maybe the level 4 multiverse doesn't contain all possible mathematical structures, but only those that are computable.
What does that mean, computable?
It means a structure that can be fully described by a computer algorithm that is guaranteed to finish its calculation and halt. This effectively cuts out the really complex, infinite, self-referential parts of mathematics where Gödel's theorems cause the most trouble.
So he's saying reality might be limited to the tidy parts of mathematics to avoid the paradoxes.
Essentially, yes. It makes the multiverse a bit smaller, but it potentially saves it from logical self-destruction.
Okay, but there's another huge problem, the one we touched on earlier, the one that, for me, is the hardest to get past.
The hard problem of consciousness.
Exactly. I can write down all the equations that describe the chemical reaction of a fire. I can describe the release of energy, the temperature, the light, but the piece of paper with the equations on it doesn't get hot.
Correct. A description of a thing is not the thing itself.
So if my brain is just a very complex mathematical structure, and my feeling of pain is just a variable in that structure called pain, why does it actually feel like anything? Why is there a subjective first-person experience attached to the data processing?
This is the famous question posed by Stephen Hawking. What is it that breathes fire into the equations and makes a universe for them to describe?
That's such a poetic way to put it. What turns the abstract math into a living, breathing, feeling reality?
And Tegmark's answer to this is perhaps the most radical and controversial part of his whole theory. He essentially says Hawking's question contains a false premise,
Which is?
that there is a fire breather. Tegmark's response is, there is no fire, the equations are the fire.
I don't, but what does that mean?
He argues that the distinction we make between a description and the thing described is just more human baggage. He claims that consciousness, the subjective feeling of being, is what a sufficiently complex information processing structure feels like from the inside.
So it's not that the math causes the feeling. The math is the feeling.
Yes, for him, a conscious being is a self-aware substructure, or SAS, and the state of being a SAS just is the experience of consciousness. The substrate doesn't matter whether it's carbon-based neurons, silicon chips, or pure abstract relations in a Platonic realm. If the structure is the same, the conscious experience is the same.
So a perfect computer simulation of my brain wouldn't just be acting like it was in pain. It would genuinely be in pain.
According to Tegmark, yes. Because being in pain is nothing more or less than implementing that specific complex structure.
That is really hard to swallow. It feels like a philosophical sleight of hand.
Yeah.
Like he's just defining the problem away.
And many philosophers and scientists agree with you. They argue that he's not explaining consciousness, he's just relabeling it. It remains, for many, the biggest hurdle for the MUH to overcome.
Okay, so let's try to bring this all together. We've gone from the surprising usefulness of math to the idea that reality is math, to this vast multiverse of all possible mathematical worlds and the challenges that come with it. Let's ask the big so what question.
Why does any of this matter?
Yeah. Is this just an exercise in wild speculation? Or does it have real consequences for how we see the world and do science?
I think it has profound consequences. First and foremost, it offers a potential answer to the ultimate question of all. Why is there something rather than nothing?
The question that has launched 1,000 religions and philosophy.
And the MUH's answer is stunningly simple. There's something rather than nothing because nothing is not an option.
Explain that.
Well, mathematical truths are necessary truths. They don't need to be created. The concept of a triangle or the fact that 2 + 2 before couldn't not exist. They exist in a Platonic sense by logical necessity.
I'm with you so far.
So if physical existence is the same thing as mathematical existence, then our universe exists for the same reason a triangle exists. Because its structure is logically possible. It doesn't need a creator or a cause. Its existence is necessary and timeless.
So existence isn't a miraculous gift. It's a logical inevitability.
That's the idea. And that completely changes the task of science. As we said before, we're no longer trying to find the one special set of laws the universe runs on. We're trying to find our address in the space of all possible laws.
We become explorers of a mathematical landscape, not just decoders of a single message.
Precisely. And it makes a prediction. If the MUH is true, we should expect to find deep mathematical patterns everywhere we look, not just in physics.
In biology, in economics, in sociology.
In the behavior of artificial intelligence.
Yeah.
If the bedrock of all reality is mathematical structure, then we should see that structure echoing up at every level of complexity. And arguably, with things like network theory and information theory, that's exactly what we're starting to find.
It's a very humbling perspective, isn't it? To think we're not special, we're not the pinnacle of creation. We're just one complex pattern in an infinite sea of patterns.
Deeply humbling. But I also find a strange kind of beauty in it.
What's the beauty for you?
It's in the frog's perspective. Even if the bird sees the whole static, determined story, we are the frogs. We get to experience it. We are the part of the universe that has woken up and is trying to read the book that it's in.
We're the mathematics that's become aware of itself.
We are the universe's way of understanding its own structure. And even if the answer is already written on the last page, the journey of discovery, the process of figuring it out, that remains real and meaningful for us, our experience is not diminished.
The search for wisdom is the point, even if the wisdom is already out there. I like that. I think I can live with being a self-aware equation as long as I get to keep trying to solve myself.
That's a beautiful way to end it.
Before we wrap up, thank you to all our partners, sponsors, and scholars who made this podcast and the research possible. We're truly grateful for your support.
And to our listeners, thank you for being part of this journey with us. If you enjoyed today's episode, be sure to subscribe and follow Stack Studios for more informative content. And support us on Patreon.
Until next time, stay curious, keep learning, and let the search for wisdom guide you forward. Have a great day.